Okay, so we're going to work through some problems from Chapter 7. These are book problems, but they are similar to the application problems in the study guide. I will do another video after this that will work through some of the more challenging problems in the study guide or problems similar to that. So let's take some of these to get started. So in problem number 36 up here, it says complete a two-line feature control frame that requires parallelism within 15 thou relative to datum feature D and a flatness tolerance of 8 thou. All right. So in a two-line feature control frame, the higher level tolerance is going to be on top of the lower level tolerance. Flatness is a lower level tolerance. It's a level 1 tolerance. Or excuse me, a level 2 tolerance, a form tolerance, or level 2 tolerances. Parallelism is a level 3 tolerance. Okay, so parallelism is going to go on top. So we'll have a parallel symbol with a 0.015 inch tolerance. Whoops, we should not include the inch symbol. Sorry. And we need to make it relative to datum D, so we'll just do a D right there. Now, it doesn't say anything about maximum material conditions, or there's certainly no diameter symbol there because it doesn't specify that it's a cylindrical feature. So that's all we need. And then the flatness tolerance, flatness, the symbol looks like that, and then it's an 8 thou tolerance. Remember, flatness does not have a datum reference, so that's all there is. Okay, so moving on to number 37, apply a parallelism requirement of 9 thou to this object. So here we have a front view, right? We're not given any other views, just this front view, and a dimension for the thickness of this feature in the front view. And it says apply a tolerance to this surface, and this is going to be the datum feature. So let's go ahead and specify the datum feature. Remember, there's a number of different ways that you can apply this. I'm just going to bring out the extension line, and I'll call this datum X. And then my feature control frame, because we're applying it to a surface, I want to go ahead and also use the extension line. And again, there's some variation here with that, but parallelism. This is a non-size feature, so I won't have any material condition modifiers. Likewise, this datum feature is a non-size feature, so there's no material modifiers here. So this is just going to be 0.009 relative to datum X. Okay, so no problem there. All right, let's move on to a similar problem. Apply a perpendicularity requirement of 7 thou to this object. So again, we have a front view or whatever view we have of this object, and it says apply the tolerance to this surface, and this is going to be our datum feature. Okay, so this is a little bit, there's not a lot of room in here, so I'm just going to pop this out on the right side and do the problem out here. Okay, so again, let's do the datum feature first. So I'll call this datum feature, we'll call that datum A, all right? And then a perpendicularity tolerance, we want to say that this surface needs to be perpendicular to A with a tolerance of 7 thou. Again, there's no material condition modifiers, right? Because this is not a datum feature of size, or excuse me, this is not a feature of size. And there's no material condition modifiers here because this is not a datum feature of size. So that's all we need to do. And just like in the last one, number 37, there's some variation for how you apply these. Just make sure that you apply it as to a non-size feature, not a feature of size. That's the only real sticky point there. All right, so moving on to number 39, apply perpendicularity requirement of 10 thou relative to 2 datums. Okay, so again, I'm going to bump this one out so that we can see more clearly what's going on. All right, so we have a front view like so, and we have a right side view. All right. And the datum features are, well, this one is the primary datum feature, and then this would be the secondary datum feature, right? Since we only have two datums. So the primary datum feature, I'll just go ahead and put this directly on the surface, and we'll call that A. All right. And then my secondary datum feature is going to be over here, and I'll just put this, whoops, like this, and we'll call that B, right? Just an extension line off of there. And then we want to apply the tolerance to this surface. And what tolerance do we want? A perpendicularity tolerance. Now, notice that this surface will be, of course, this surface right here is perpendicular to A, right? But is this surface also perpendicular to B? And the answer is yes, because this surface right here, the one that we're going to apply the tolerance to, is this surface here. And that is perpendicular to A and B. So that's why we're allowed to do this. You know, I'll make things a little bit different here. We'll just apply that with an arrow. You could also apply it with a extension line like I did up here. So perpendicularity, and it's 10 thou relative to A primary and B secondary. Okay, and again, this is not a datum feature of size, so there's no material condition modifier here, nor is it a cylindrical feature, so no diameter symbol. A and B are both non-size features, so no material condition modifier here. Okay? All right, so moving on to the last one on this page. Apply an angularity tolerance of 12 thou relative to the two datums. All right, now I'll go ahead and do it in this drawing because I think there's enough room. So we have a primary datum here and a secondary datum feature on the right-hand side in the right-hand side of the right view. So we can call this X, and we'll call this N. Okay, right? Remember the numbering or the lettering doesn't matter. And then we want to apply it to the tolerance to this surface. So for angularity tolerances, maybe the easiest thing to do is just use a leader. And I didn't give myself enough room there, but we'll make do. Angularity tolerance, 12 thou, 0.012 relative to X primary. And secondary, again, no features of size involved in this, but do not forget, we must specify the angle for this surface as a basic dimension. So the angle relative to the datums, must be basic dimensions. All right? So this needs to be a basic dimension. So we need to put a box around that. All right. Now this N would also be a basic angle of 90 degrees, right? 90 degrees to this inclined surface that we're specifying with the tolerance zone. But 90 degrees basic is understood. Okay, so we don't need to specify that. It would not be wrong if, however, you did that. It would be weird, but it would not be wrong if we did like a 90 degrees basic like that. And that's really the only view you could do that, all right? But you normally would not do that, all right? This, yes, you would do. You must do that. All right, so those are the first 5 of these. Let's move on to the last couple here. All right. Now I'm going to skip on some of these, and we'll do those. We'll do some of these with another video here. But let's go ahead and look at number 42. Okay, apply a perpendicularity tolerance to control the pin within a 5 thou cylindrical tolerance zone at MMC relative to the datum feature. Okay, so now we're talking about, well, it mentions MMC, so and we're talking about perpendicularity tolerance to control the pin. A pin is a feature of size, right? It's a positive cylinder. So how we specify this on the drawing? Let's see if I can do this right here. I think I should be able to. So we got to draw this again. All right, and we'll put in the size dimension. Diameter 375 plus 2 thou minus 1 thou. All right, and let's first do the datum feature. This is a datum non-size feature, right? So we just want to call this out and say, hey, that is, we'll call that C, right? So that's datum C. And now we want to apply a perpendicularity tolerance to the pin with a cylindrical tolerance zone. So now you need to get everything right. So we're applying the perpendicularity tolerance to a feature of size, so it has to be associated with the size dimension, which we're doing by hanging it underneath there. We have a perpendicularity tolerance. The feature is cylindrical, so the tolerance zone we want is cylindrical, so we need to put a diameter symbol there, 0.005, and it says at MMC, so circle M, and then relative to datum C. Okay, and datum C again is a non-size feature, so there's no material boundary conditions that we need there. All right, so that's number 42. We'll skip number 43 for right now because that involves me putting some sketches in there, and we'll do that with some other problems in the next video. Okay. Another similar one, apply a perpendicularity tolerance to control the hole within a 7 thou cylindrical tolerance zone at MMC relative to the datum surface. Now, the only thing different here in number 44 versus 42 is we're talking about a hole here. Nothing else changes. So we want to call this out as a datum feature, so we'll do it right there. We'll call that A. Okay. And then the feature control frame. So one way we could use the feature control frame is to hang it underneath the size dimension here. We can also extend the dimension line and put it in there. So we want a perpendicularity tolerance. It's a cylindrical feature, so we need the diameter symbol, 0.007 at MMC. I didn't give myself a lot of room. Relative to A. Okay, so there we go. I hope you can see that. All right. And again, 45, we'll skip that because we'll do that again in the next video. Sketch 1, acceptable configuration for the part. Again, we'll skip that. I think we're going to do a bigger problem more related to the study guide problem, so I'm going to skip that also. And then make the necessary changes to apply the shown tolerance to a tangent plane. Okay, and we'll skip that one too because I know that we'll be doing some. So the only two that we did here was the problem number 42 and problem number 44. And since I'm still, there's some other stuff that we can do for 42 and 44. So let's look at 42. What is the virtual condition size of this? So the virtual condition size, this is a positive feature, right? A pin is a positive feature, so I'm going to put a little plus there. The virtual condition size is the size of the feature at MMC plus the tolerance at MMC. All right, positive feature plus, I shouldn't put a minus sign right there or a little dash there, you might get confused. Okay, so the size at MMC, this is 375 plus 2, or 377, right, for a positive feature. And then tolerance at MMC, well, it says right there, it's 5. So the virtual condition of this is 0.377 plus 0.005, which is 0.382. Okay. Now, if we were actually going to go on and do number 43, sketch and dimension a theoretical functional gauge to check the part, in problem 42, show your calculations, that would be it. So my functional gauge would be a like this. I kind of hesitate to do this because I just don't have enough room. So let's say it was going to be like a cylinder with a hole in it, and the hole right here is going to be a diameter of 382. Okay. Likewise, oh, and notice that this would rest right on datum C, this feature. Now, if we do, and I think problem number 45 says the same thing, kind of the opposite here. But if we look at this, the virtual condition for a negative feature is equal to the size at MMC minus the tolerance at MMC. In this case, the size at MMC is 0.5 minus 0.005, or 0.495, minus the tolerance at MMC is 7 thou, 0.007. So this is equal to 0.488, I believe. All right. And then it says sketch and dimension a theoretical functional gauge. So how would we check this? Well, what we could do is we could make this a functional gauge that looks just like this, right? And this diameter would be equal to 0.488, right? And this would be flat. And so that would be our functional gauge. So basically what we would do is we'd grab these off the assembly line. You know, let's pretend there's an assembly line that's making a whole bunch of these. We'd grab them and we'd have this gauge in our hand, and we'd take the object, and if this gauge, if this pin with this flat surface went into this hole against this surface right here, the datum feature, then it would be good. Now think about this. Look at this. The smallest hole size is 0.495. Okay, but this pin is 0.488. So you'd think that will fit, right? A 488 pin should always go into a 495 hole, minimum 495 hole. But remember that the virtual condition takes into account the size and in this case, the perpendicularity tolerance. So as long as the hole is not out of perpendicularity by more than 7 thou at MMC, you know, then this will fit in there. All right. Just one more thing that we can kind of specify here while we're looking at this. We can make a little table. I'm going to do this in the other video too. I know this is a big part of it, but and we can make a column for the size, and we can make a column for the tolerance, right? And we know that if the size is 495, right, which is the MMC size, then the tolerance at MMC is 7 thou. Okay. If our size deviates from 495, and which way can it deviate? It can go up. So we can have, let's say 5, I'll skip a few, 500.5. This will be 0.012. Why? Well, 0.5 minus 0.012 equals 0.488. And remember, this is a constant. If we go all the way up to, if we make the hole at its largest diameter, 0.505, then the tolerance increases to 0.017, right? Because 0.505 minus 0.017 equals 488. Okay? So that's a quick little table that you can do. Obviously, the values in between this are going to be in between these tolerance values. And we'll do more of this in the next video. Okay? All right, so I'll see you in the next video.